For our Minimax algorithm, we decided to implement two functions that would recursively call each other, because the assignment recommended a recursive approach. Both functions return the highest value in terms of the max function and the lowest value in terms of the min function, and in which column this occurs. This means that this is likely the optimal column. They start out by checking if we have reached the max depth or a terminal state, meaning there is a winner or a draw, and if this is the case, we immediately return the score and no optimal move. Then we check every child of the current node to retrieve their scores, and we keep track of the highest score in case of the max function and the lowest score in case of the min function, and we return the column in which this occurred. This propagates all the way back up to our make move function, which just returns the column.
In addition to our Minimax algorithm, we created the AlphaBeta class. This class shares most of the same code of our Minimax algorithm, with a few key differences. The AlphaBeta algorithm has a second base case in a recursive step. In this base case, A is compared to B in both min and max move. If A is bigger or equal than B, the current node is pruned because it would not change the final output. In min move, the if statement checks if B is smaller or equal than A, which would also prune the node. Thus, both these base cases serve as a pruning step where further nodes will not be explored, because they would either not be the minimum or maximum value.
For the Monte Carlo algorithm, we first defined the structure of the game tree using this class Monte Carlo node. It contains the most important information, including what its parent and children are, the current board state, how many times it was visited and how many of these visits resulted in a win, and which children haven't been discovered yet. It also contains the logic for selecting the best next move based on the upper confidence bounds applied to trees. This is a formula that gives each child a score based on the win rate, which is the exploitation part of the formula, and how often the child has been visited compared to the current node, which is the exploration part of the formula. The amount of exploration can be fine-tuned using this exploration constant, and we picked the square root of 2 for this value, because we found online that this is often the default, but we also found that this value is meant for values between 0 and 1, but we decided to keep it, because the algorithm seemed to work well. As for the Monte Carlo player itself, this contains the 4 default steps of selection, expansion, simulation and backpropagation. The first stage uses the best child selection formula from before to pick which path to take in the search tree for already discovered states, and when it picks a child that hasn't been discovered, it expands to this child and simulates a random game from this point onward, after which it propagates weather at 1 back up the tree, updating every node along the way. It repeats this for the amount of rollouts we defined, and finally it returns the child of the route that has been visited the most, as this is likely the node with the highest chance of winning.
And lastly, we created a more advanced heuristic. Our heuristic gives more value to the middle columns over the outside ones. We did this by assigning a value to the distance between the player's move and the center of the board, with pieces close to the center getting a higher score. This new heuristic encourages the model to make strategically better moves, having more control over the center. Thank you for watching, stay tuned for our next assignment, Sudoku.